All right, we're now talking about thunderstorms in earth science. We're in chapter 13, section 1, if you're following along in the book. And we're talking about thunderstorms. We've already talked about fronts. We've talked about weather patterns. We've talked about climate. We've also talked about air masses and the atmosphere. And so now we're going to specifically focus in and talk about thunderstorms and how they form, what types of thunderstorms there are, and the local conditions that create them. The essential questions for this section you should be able to answer by the end of this presentation. How do thunderstorms form? What are the different types of thunderstorms? And what is the life cycle of a thunderstorm? Your vocabulary for this section is, as shown here, air mass thunderstorms, mountain thunderstorms, sea breeze thunderstorms, frontal thunderstorms, stepped leader, and return stroke. And those last two are specifically referring to lightning. All right, I have this image here, and this map is basically showing average number of thunderstorm days annually for different areas of the United States. In your textbook, it's a lot easier to see. You can actually see numbers where you can see the breakdown of where exactly they are between 10 and 30 thunderstorm days annually. But what this means is annually is per year, and this is telling you how many days per year there's at least one thunderstorm. And so if there's multiple thunderstorms in one day, for example, that's still just one thunderstorm day. And as it shows here, the white is any state or any area that has less than 10, so 9 or less. And then the yellows are all 10 to 30, the greens are all 30 to 50, and then the oranges are all 50 to 70. Anything red, like here and here over by Florida, this is all more than 70 annual days of thunderstorms per year. So if you love thunderstorms, you know where to go. And they are beautiful. I don't know if I'd want them every day or every third day, but yeah. So how thunderstorms form? For a thunderstorm to form, 3 conditions must exist. The first is there must be a source of moisture. There must also be a lifting of air mass, and there must be an unstable atmosphere. So in order for a thunderstorm to form, those 3 conditions must exist. Just because they exist doesn't necessarily mean you're going to have a thunderstorm. So note that. But in order for a thunderstorm to exist, these 3 conditions must have been met. So going into detail about the first, there must be an abundant source of moisture, and typically we're talking about the lower levels of the atmosphere, closer to the ground. The second thing was there must be some mechanism for that moisture to condense and release its latent heat. And usually we're talking about different types of lifting, and we'll talk about that in a minute. So like it says here, this occurs when a warm air mass is lifted into a colder region of the atmosphere. And this is true because typically warmer air holds more moisture. The ability for it to hold moisture is increased as it's warmer. So the third thing that has to be met is that the surrounding air needs to remain cooler than the rising air mass. As we know, cold air is more dense than light air, and light air floats on top of cold air. So in order to push up warmer air, the surrounding air mass has to be cool. And we'll talk about this typically is related to fronts and or orthographic lifting, but we'll go into that in a minute. So limits to their growth. Because of the rate of condensation diminishes with height, most cumulonimbus clouds are limited to about 12,000 meters. And you'll see as you approach the upper limits of the troposphere, because in the stratosphere temperatures start increasing as you increase in elevation, it's going to create a limit on how high this buoyant effect can lift you before there's this inversion that makes it so it's impossible for you to go any higher because you kind of get capped out. They're also limited by duration, and we'll talk about the release of energy, which will help that make more sense. Thunderstorms are often classified according to the mechanism that causes the air mass that formed them to rise in the first place. And this breaks down into 2 different types that we'll talk about. So thunderstorms will typically be either air mass thunderstorms or frontal thunderstorms. An air mass thunderstorm. So when an air mass rises because of unequal heating of Earth's surface beneath one air mass, the thunderstorm is called an air mass thunderstorm. So we talked about source regions and air masses and how when you have an air mass, it rises above the source region or rises out of the source region because it's the same temperature, but the surrounding air is cooler. And so it gets buoyed up and it just causes this blob of air to rise up. Kind of like a lava lamp. If you've ever seen a lava lamp before, there's a heating device on the bottom of the lava lamp, usually just a light, and it heats up the waxy substance, and as the waxy substance gets warmer, it liquefies, and it eventually starts rising up amongst the surrounding fluid. And the surrounding fluid will typically be slightly cooler than the rising mass in the lava lamp. And that's an easy way to visualize what's happening in the atmosphere when you have an air mass rising around a source region. And this has the potential to cause a thunderstorm in the larger sense. Mountain thunderstorms occur when the air mass rises by orthographic lifting. We talked about this with Hawaii. A better example of this, because we don't want to confuse an ocean interface with this. So when we're talking about mountain thunderstorms, we're typically just talking about land. So they have flat land, like a flat valley, and air is rushing across that flat valley that has some moisture in it, and it's forced to rise up through orthographic lifting. This is like a ramp. So I want you to imagine you're minding your own business, riding your bike, and you don't realize that there's a ramp right in front of you. You hit that ramp, and that ramp is going to cause your direction to head up in elevation. You're going to jump off of that ramp. So air will behave the same way. Air slams into that mountain face, and it has no choice but to go up. And as it rises in elevation, this is called orthographic lifting, which causes the elevation to increase, which causes the temperature to decrease, which causes that water moisture that was in the air to precipitate out. And if it does it rapidly enough and it's able to accumulate charged particles in the upper atmosphere, you can end up with a lightning storm. Or usually you'll end up with a cumulative cloud. Sometimes that can result in a thunderstorm if it happens rapidly enough that it can form before the charge dissipates. The other type is sea breeze thunderstorms. So sea breeze thunderstorms is where you have this ocean or lake interface with land, if the lake is big enough, and you'll have a local air mass thunderstorm that occurs because the land and water store and release thermal energy differently. And let me just show you a picture, because that was kind of wordy. So I want you to look at this picture here, and in the first picture we have the sun out, and the sun is heating the ground faster than it's heating the ocean. And this mainly has to do with the heat capacity of water, but I'm not going to go into detail with that because this isn't a physics or chemistry class. This is an earth science class. So just trust me that the sun is going to heat up the ground faster than the water. If you've ever gone to the beach, you'll know that the sand heats up faster than the ocean. Okay, and as it heats up, it's going to be a higher temperature, and so the air directly adjacent or directly touching that land is going to rise faster than the air that's above the ocean, which is going to cause this cycling trend of warm air rising. And then as the air rises, air rushes in to take its place from the ocean, and you get a sea breeze coming in from the ocean. And at nighttime, as the land temperature drops, the water temperature is going to remain roughly the same, and the cycle is going to reverse because the air is going to be lifting. Because of this difference in temperature, the air is going to be rising from the ocean faster than it's rising from the land, because the ocean will be warmer than the land. And so the trend will reverse. You'll have a land breeze where air is coming off of the land towards the ocean, reversing the cycle. And you can imagine if air is rising, it has the potential to create a thunderstorm or the potential to create precipitation. So if that rising is happening over land, you'll have the thunderstorm occurring over land during the day. And at night, when the trend is rising over the ocean, you'll have the thunderstorm forming over the ocean. Okay, that's a very simplified explanation of what's happening, but that's the general idea. All right, so the other type of thunderstorm is going to be called frontal thunderstorms. And frontal thunderstorms is referring to fronts. We've talked about fronts already. We talked about cold fronts and warm fronts and occluded fronts and things like that. And if those end up causing air to rise and cause a thunderstorm, we call those frontal thunderstorms. And they're typically caused by advancing cold fronts. So we talked about fronts, and the front is the air mass that's advancing, the air mass that's in motion. And so if a cold front is advancing and meets warmer air, it's going to act like a shovel, like a snow shovel or like a ramp, and it's going to force that air mass to rise. The cold air is going to come in, and if it strikes other air, it's going to cause that warmer air to rise up above the cold front. And it's going to push it up to higher elevations, and as it gets pushed up to higher elevations, depending on how rapidly this is happening, you have the potential to cause precipitation. If it happens rapidly enough, you release that energy fast enough, you result in thunderstorms. And I'll talk about how this develops. So a thunderstorm usually has 3 stages. We have a cumulus stage, a mature stage, and a dissipation stage. And sorry, I'm talking a little fast. I just want to make sure I can get through to the stuff that I need to, and I'm trying to keep this under 15 minutes. So anyway, cumulus stage, mature stage, and dissipation stage. So in the first stage, the cumulus stage, we have the formation of this cumulus cloud. And as the cumulus cloud forms, as some of that moisture precipitates, that latent heat will be released, and that thermal energy that's in the latent heat will be allowed to once again cause that rising air mass to cause more precipitation. And as long as there's more thermal energy to fuel this process, it continues forming more cloud mass. Okay, and eventually you get to what's called the mature stage. And at the mature stage, you have updrafts of warm air rising. You also have downdrafts that are forming a convection cell which produces the surface winds associated with thunderstorms. We've talked about convection, and you know with convection, hot air rises, cold air falls. And as long as this is decoupled, where they're slightly off of each other, there's not quite as much interference with one trying to cancel out the other, and you can actually fuel this process. And as long as there's a source of warm air feeding into this, you can continue with this formation and fueling of this thunderhead. And something interesting that happens sometimes when you get this decoupled too much, where the updraft is too far off to the side, you'll actually fuel this so rapidly that sometimes you can form a supercell and you'll get a tornado. So anyway, this is going to be happening until this cuts off, and once this cuts off, we call that the dissipation stage. And you'll notice that from the previous slide, that updraft has stopped. There's no more warm air rushing into this, and so this energy is going to be released and consumed, and then it's going to basically slow down and stop. And I like to compare this to like the boiling of water. If you have boiling water on the range, as soon as you turn the heat off, you can see the boiling slow down and even stop, because you've stopped putting energy into the storm. Next up is lightning. So lightning is the transfer of electrical charge caused by the rapid rushes of air in a cumulonimbus cloud. So let me go back to this picture right here, and I want you to imagine this air is creating friction, because this rising air is sometimes bumping into this falling air, and there's a lot of transfer of charged particles. Also, this incoming front is also running across the ground, potentially picking up charges from the ground. So there's a combination of picking up of charges. And if this is happening rapidly enough, you can accumulate enough charge up in the atmosphere where you have a charge gradient. And once that charge gradient is high enough, you can actually produce a potential. And if that potential gets high enough, you have a potential or a voltage. The word voltage just means potential. And if your voltage gets high enough, then you can actually connect an electrical arc from the sky to the ground, and that's what lightning is. It's this static charge differential that's caused and results in lightning. So lightning is pretty cool. You have some different words we're going to talk about. One of them is a stepped leader. So once you have enough charge, the dielectric of air ends up breaking down, and you're able to send that that difference in electrical potential from the sky to the ground. In the first part, you actually create a channel of plasma or a partially charged air, and they call this a stepped leader. And you can see this in like high-speed footage of lightning strikes, where you'll see like a really skinny, looks like a skinny lightning bolt forming first. And then once the air is all ionized, it creates an easier path for the lightning to follow. And then you'll get that large channel of energy released that'll be that light, that really bright flash that creates that shock wave. And that characteristic shock wave is what we call thunder. And you'll actually have a return stroke as well, where you'll get energy going back up. And they've actually showed that you can probably actually find footage of this return stroke and stepped leader happening multiple times before you actually get a channel forming. Or sometimes you'll have a channel of energy that comes down, and you'll actually see it either going up and down or back and forth a couple times, releasing all that energy. The lightning bolt heats the surrounding air to about 30,000 degrees Celsius, which is about 5 times hotter than the surface of the sun. The thunder you hear is the sound produced by the superheated air rapidly expanding and contracting. So you get the shock wave, air is expanding outward, and then as it expands outward, it cools, which causes a vacuum, and it causes it to go the other direction. And that those two back-to-back shock waves are what produces that sound that we perceive as thunder. So we have several different names given to lightning effects. They can call it shear lightning, heat lightning, spider lightning, ball lightning, blue jets, red sprites, other things like that. And that's just plasma in the atmosphere. So yeah, here's your review. Remember your essential questions, remember vocab. Thanks for watching, and don't forget to subscribe.